Hello everybody, my name is Andy Roberts. I'm from Desktop Metal, and today I'm going to show you some of the latest features of Live Sinter, which include a new and revised workflow, as well as I'm going to show the process for not only generating your first parts, but also how to use the scan adjustment feature to correct parts after you have used Live Sinter. So to begin this, I'm going to start out by showing you some images that illustrate the workflow of Live Sinter. And the first image is going to start out by showing you how you essentially create a model in Live Sinter and use it to generate the negative offset geometry that you print. So on the top left, we have a new model where I've added a part zone, which is the blue shape. This represents the shape of my CAD part. No scaling, no nothing. It's just what I bring into the sintering environment in order to simulate how this is going to shrink and deform. And the purpose of this is so that we can then offset it, not only scale it up to handle the shrinkage, but also to deform it, what we call a negative offset deformation, to compensate for the warping that may occur. The first thing that we do in Live Sinter is we fill the part area with cells. That's what you see in the second image, the dark blue cells. The next step is we apply what's called a scale-up operation. And scaling up the part is essentially what you would do if you were using just a tool like Fabricate Manufacturing or a third-party tool to apply scaling dimensions to make the part larger in X, Y, and Z to compensate for the shrinkage. The first thing that Live Sinter does is it scales up your part so that it will have a good beginning point to run the simulation. We know it's going to shrink, so we may as well scale it up. Then what Live Sinter does is it runs the simulation of the sintering, which is the third or the fourth image. And when it's finished, the part will have shrunk, but you can see in that image that it's also distorted. This is because it had friction contact with the ceramic setter, which is shown in red, and it caused it to warp unevenly. Live Sinter performs something called a deviation analysis, which compares the final shape of the part. This is the image in the center. It's comparing the final shape of the part after the sintering simulation with the original shape, which is the blue part in the top left corner. And it's showing us that the deviation is horrible, that it's really way out of shape. So what Live Sinter does next is applies a negative offset, which goes back to essentially the same shape as the scaled up part, but you can see that it has compensated for the warping that took place as it shrank by altering its shape. We call this a negative offset shape. And you'll notice that in particular the part when it shrank, the foot on the ceramic setter did not move as much as the top of the part. So it kind of shrunk to an open shape. And as a result, the negative offset is compensating by creating kind of a closed foot. It kind of looks a little weird, but this is the process. So after we've generated the negative offset, Live Sinter will ask the question whether the deviation that it saw before was close to zero or bad. Now in this case, going back to our center image, it was horrible. So that means that the answer to this question is no, and it goes back to the run sintering step using the negative offset shape, and it runs the simulation again, and it generates a deviation analysis, and it applies the negative offset again. And if it gets to this point where the deviation from the previous time it was run to the current time it was run has shown no difference, no change, then it means that the negative offset has achieved the best shape that it can to create a result that will match the shape of our original part. And if this is the case, then Live Sinter will save the model and export the negative offset shape in the form of STL. And this will be smooth and contain all of the details of your original part, which you can see in the exported STL. And notice that's the part that has the kind of toed-in foot, as we call it. And if we put this in the printer and print it like this and then sinter it, it will come out straight, as in the picture on the lower right, which is an actual Live Sinter part that was printed like that and came out of the furnace. So with that, what I want to do is just show you quickly in Live Sinter what this workflow looks like. So what I have here is Live Sinter running. And the first step is to do something called adding a zone. And we can add parts, we can add supports. These are both made out of the metal that's going to shrink. We can add setters if we want, although we typically like to let Live Sinter generate the setter. The setter is the ceramic plate that goes underneath your part. We can also generate scans, which I'll show you later. So in this case, we have a simple part. We don't have any support that we've created in advance. Sometimes you'll want to bring a part in and just put it on the setter. Sometimes you'll want to bring a part in and you'll want to auto-generate a support, in which case I would check this box underneath it. This is new functionality, so it's undergoing lots of changes. Other times you may want to begin by bringing in the support and auto-generating a setter, and then you'll go back and you'll bring in a part and you won't generate the setter. So you'd bring in the support first, place the setter underneath it, and then you'd bring in the part and it would go on top of the support. I'm going to just bring in the part directly and generate a setter underneath it. Now you should save these parts in the orientation that you want them sintered in. Now let me go ahead and bring this in and you'll see what I mean. So this is bringing up a dialog box where I select a file. I can bring in step files and STL files. So I'm going to bring in my calibration slug, that's what this part is called. And you'll see that it is oriented with the Z direction up. This is the direction that sintering takes place in. Z is up, the blue arrow. And it's a good idea for you to save your parts and your supports in advance in the orientation with Z up, because when they come into Live Sinter, they come in the correct orientation. So at this point, what I could go ahead and do is fill it in with cells. This is to get it ready for the sintering process. But before I do that, it's a good idea to check on the cell size. You'll see here that the cell size is recommended to be between 0.68 millimeters and 0.85 millimeters, and it's recommending that the cell size be 0.75, somewhere nice in the middle. It's a good idea just to go with the default values. That's what you typically want. At this point, you'll see that I have the ability to add additional zones if I want. I have the ability to run this fill zones function, and that's what I want to do. This is going to go ahead and fill the part in with cells. The point of the cells is that they are the shrinkable, deformable material that simulates what happens in the furnace. The blue shape that I have is there for reference purposes, so it's not going to shrink and deform. It's going to stay that shape, and that's useful because when Live Sinter runs, it will essentially change shape. The cells will shrink and deform. And it's very easy for Live Sinter to compare that shape to the original blue shape to see if it's done a good job in generating its negative offset. So keep that in mind. The blue parts and supports that you bring in are references, and the cells fill those shapes in, and then the cells are what actually get scaled up and shrink and deform. So I'm going to let this process go ahead and complete, and then we're going to go ahead and run the sintering simulation. Okay, now we've completed the process of filling in the zone with cells. And so we're going to perform the first step of the process of sintering, and we're going to do this manually. The reason I'm walking through these steps manually is so that you can see how it works. Later I'll show you that you can actually bypass all these steps by just clicking Run Complete Cycle, and it will do everything. It will scale up your part, run the simulation, apply negative offsets, iterate the whole process until it comes to a nice steady state, in which case it will export your finished part. But we're going to go through this manually just now so you can see the process that it takes on internally. We're going to do this apply scale up operation. One thing I should point out before we go ahead is that I forgot to mention that before you fill in the cells, it's a good idea to select either the shop or production system profile parameters. If you're going to be running this on the shop system, you don't have to touch these values because they're already set by default. But under the parameters section, we have a whole set of parameters that are set when you click on the shop 5 parameter profiles. Like I said, this is set by default, so you don't actually have to click it, but if you're curious to see what's going on, that's what's happening. Okay, so now what we're going to do is apply a scale-up operation. And this is going to scale the part up by the scaling factors that Live Sinter uses for this particular material. And you can see now that the part has grown in size. Let me just look at my display here. And if you look down in the center, you can see that the original part shape is still there. So the part has gotten larger. So this is what would happen if you were to scale it up linearly in a system that did not take sintering simulation into effect. And so the next thing we're going to do is run the sintering simulation. So Live Sinter will run through a sintering cycle. It will start out at the temperature of the furnace when it starts, but Live Sinter is actually going to run the simulation starting at about 600 degrees centigrade, because this is the temperature at which the debinding has essentially completed and the actual formation of the part takes place. Now you can see the process of the sintering simulation begin. This process usually takes about 5 to 10 minutes to run. It depends upon the complexity of the part. This part has about 75,000 cells, which is not too big, so it's about in the time frame I mentioned. You can have parts that will have cells up in the range of 200 to 300,000 cells, in which case it might take 15 minutes to run a simulation. You can also have parts that are smaller. It's kind of a function of the cell size and the number of cells. The smaller the cells, the more time it takes to solve, and the larger number of cells you have, the more time it takes. So not much is going to happen in this right away, because until we get up to about 900 degrees centigrade, there's really not much shrinking taking place. In fact, in some cases, due to certain materials, they'll actually swell up a little bit. But once it gets up into the 900 degree range, we start to see some active shrinking taking place. Now during this process, if we want, we can click the pause button, which will just temporarily pause the sintering simulation. If we wanted to, we could also stop the sintering process altogether and then restart it. There's really not much reason to do that, but you could do it if you wanted to stop the process and do some sort of an analysis on it, or let's say you had forgotten to set the parameters properly, you could set the parameters and then continue running. Or if you wanted to save the model and go home and come back and open it later and run it, you could also use that operation. A couple of the things you can do while you're displaying this, you can look at different view types. So under View Show, we have here, under Display we have the ability to see this color is the strain. Another thing that's interesting is to show the density. If I select density and then rotate this part a little bit, we're going to see that in this orientation, the x-axis is pointing to the right. When parts are printed using the shop system, the print head moves from right to left in the negative x direction. And as the powder spreader moves in the negative x direction, it lays down slightly higher density shells on the leading edges of the part on each layer. And that's why you see a slightly lighter blue color. That's important because when parts shrink with slightly higher densities on these faces, if there are thin features on these parts, it can cause them to warp. And in cases like a cylinder where you have a higher density on one side, you'll get what we call the leaning tower of Pisa effect, where the part warps towards the area of lower density, which is on the trailing edge of the part. And then Live Sinter will compensate for this automatically. Another view operation that we have here is under Display, is we can look at the stress. And if you look at the stress, you're seeing the areas where the stress is the highest in the part. And the importance of stress is that plastic creep strain is triggered in areas of high stress and high temperature. And plastic creep strain is what I like to think of as the taffy in the hot sun effect. When the part is shrinking, it has a lot of bending resistance, which is due to the elasticity of the part. But at a certain temperature and stress, the part will break down, and it's no longer going to have an elastic effect. It's going to have plastic deformation, which causes permanent deformation to take place in the part. So that's what we're seeing here is the areas of high stress. Another thing that's interesting is that the friction of this part on the setter is causing it to open up. If we look at it from the top, you can see that the foot or the base is dragging on the setter, and the top of the part is closing in because of the shrinkage of the top. This is something we call a phenomenon of C-shaped parts, which are parts that have irregular shapes on the setters tend to shrink in ways where they drag on the setter in an uneven, non-uniform way and cause a lot of deformation to take place throughout the part. This is nearly impossible to compensate for in any way with your geometry, and that's why Live Sinter does this automatically. Now, some people would say, well, why don't we just put some kind of a support underneath that that's like a round plate, a disc essentially, and you could do that, and it would probably get rid of a lot of this deformation. On the other hand, if you're looking to minimize the costs of your 3D printing, and not only the cost of printing, but the cost of depowdering and having extra parts, it's very powerful to be able to compensate for deformation using Live Sinter rather than trying to essentially eliminate the deformation, which can sometimes lead to cracks and definitely to higher costs. Right, so I'm going to go ahead and let this finish. Okay, so you can see that we've completed the process of the sintering. The temperature has now reached 0. And if you look at the part combined with the view of the original part, you can see that the part has deformed a huge amount. This would be a total disaster if you were to print and sinter this without using a support and without using Live Sinter. But the good thing is that we have a couple of tools to help us compensate for this. The first one is something called Analyze Deviation. And when we use Analyze Deviation, it's asking us it's going to compare the shape of the part to something else. And it's going to ask us if we want to compare the regions of this part or point level. This is really a level of granularity question. Usually it's good to look at the regions because it's faster. The next thing that we're going to do is go ahead, and there's only the part in here as opposed to having a scan, which I'll get to later. It's going to ask us to just go ahead and specify a few parameters to indicate the size of the deviation, as well as the size for the purposes of showing the scale, as well as the region size. Now I know in this part that there's a huge amount of deviation, so I'm going to specify this deviation threshold to be 2 millimeters because I want to see essentially the deviation spread out over a scale that shows just how bad this is, with blue being very little deviation to red being huge deviation. So what this is doing internally is fitting the part shape to the finished sintering run. And once finished, it will then calculate the deviation of the different patches on the part to the original part shape, and it will show this in a color-coded way. And this is what Live Sinter does internally when you run the complete cycle. After each sintering run, it compares the shape of the final part to the shape that it should be, the original part. And if these get to be very close, then it applies its last negative offset and stops. If it's not very close, then it applies a negative offset and it continues. And each time it applies the negative offset, it's tweaking the previous negative offset. So this process converges in on a nice final shape that will give you 0 deviation. Now that the deviation analysis is complete, we can take a look at the results, and you can see that on the scale of 0 to 2 millimeters that we have some areas that have very high deviation, especially these areas in yellow. You can see the deviation is over 1 millimeter. This is obviously bad, and so we would want Live Sinter to compensate for this by applying what's called a negative offset. So we can dismiss these results by clicking Dismiss Heat Map. This goes back to showing us the final shape of the part. And at this point, what I'm going to do is apply a negative offset. And the negative offset is a complex calculation that Live Sinter performs by comparing the final shape of the part to what it should be and going and tweaking our initial scaled up model so that we get a shape that will result in something much closer, that sinters much closer to the desired shape. So you can see here, this is the first negative offset. So if I were to run this again, the shape would become closer to the desired shape, and it would take 3, maybe 4 times of iterations for this negative offset to produce a final shape that was desirable, matching the exact shape of the original part. So let's say that we had fast forwarded through these steps. I would do a file save operation to save it, and I would do an export STL operation to export the STL files. The save operation saves the model that produced this whole thing. It's the intelligent model that knows how to run simulations. We call those .lpi files. The export is taking an artifact from this, the STL from the negative offset shape that you see on the screen, and it's exporting it for printing. And I should point out that if you have fine details on your original part, they get transformed in the export. So don't worry about the fact that you see some Minecraft stair-stepping in your part in this simulation. That is not transferred to your part on export. So that's how you essentially run the live sinter process and get a part that's ready for printing. Let's say though, if we go back to the image that we had before of our presentation, let's say that in this case we printed the part out and we sintered it, and the result came back a tiny bit off. Let's say that it was off by 1/10 of a millimeter, or 100th, not 100th, but a tenth, maybe 40 microns to 1/10 of a millimeter off in different places on a part this size. Well, we have an ability to correct for that. And what we do is we open up the model that we had created, which we just created essentially the first step of that with the first negative offset. And we scan our part, and then we load the scan into Live Sinter, and we use something called a scan adjustment, and that tweaks or massages our original negative offset to make it compensate for the small errors that we may see in the scan. And then we export that again. And when you print and sinter that, you'll get something that's very, very close. So let's go ahead and take a look at that in action. I have another copy of Live Sinter here running. That's why it may have been a little bit slow this whole time. It's because I'm running 2 copies on my machine. And you can see here the negative offset count is 5. So this is actually the part after it ran 5 iterations, the scale up, and then 4 sintering simulations with negative offsets to get the shape that was printed. And this created quite an accurate shape, but it wasn't perfect. It was off by about 1/10 of a millimeter in different places. So we have an ability to load the scan in. And the first thing I like to do, though, before I load a scan in, is usually clean the scan up a little bit. And I don't mean clean it up because it's got, bad data in it. I mean it has too much data. So what we typically do is we scan using a number of different scanners. Riven is a very nice one. The GOM scanners are scanners that we also use. We scan and usually get files that are fairly large. And sometimes you want to clean these up or decimate them to get rid of some of the data. What we're going to do in this case is show you the calibration slug scan full size. This was 82 megabytes, which is too. You can bring that into Live Sinter, but it's undesirable because it's too large. What Live Sinter is looking for is the shapes in the deformation. It's not looking for the super fine resolution points that you get in a scan. So what you typically like to do is take a scan that's like 80 megabytes and blast it down to something like 8 megabytes. So I use MeshLab, but you can use tools of your choice. And if you go under Filter, this is a free tool. So if you go under the Quality Measure and Computations, Remeshing, Simplification, and Reconstruction, and go down to Quadric Edge Collapse, if you were to click 0.1 and apply, this would essentially remove 90% of the points from your scan and still keep the shape of your scan, which is essentially what we need with Live Sinter. That's it. So what we do is we say that we want to add a zone, and this time we select scan. And we're going to associate the scan with our part. We want the two to be tied together inside Live Sinter. This is important because you might also have a support, and you want to bring in the scan of your part and associate it with the part as opposed to the support. So you can see here that I have calibration slug scan and then the full size, and the smaller one is the result of doing that 90% decimation of data. So this is going to bring in the scan file, and I will then have to do a step of placing it, rotating it around and getting it sort of into the right orientation. And this is because we want to help Live Sinter do the process of positioning the scan relative to the part, make that as easy as possible. You can see that it came in here kind of upside down and twisted around. We can go ahead and right-click on the scan and select Edit Transform, and then we can apply different rotations here. Now, since the x-axis is pointing towards me, I would like to rotate this a little bit more than 180 degrees in the x-axis. I want to sort of rotate it about the axis pointing towards me. So I'm going to use the Control button and then left-click on Rotate, and I'm going to click 182. And then I'm going to do an Apply. And you'll see the part flips around. Now you can see that it's pretty close, but I'm going to rotate it about the z-axis. I'm going to rotate it by essentially minus 18, 20 degrees, something in that range. And that's going to twist it. Oh, I'm sorry, I did translate. So I'm going to just push that back up and do rotate about the z-axis by minus 18. All right, and then we do want to move it in the z direction. I think I'm going to move it up about 20 in z. And then if I look at it from the bottom, I want to move it a little bit down in x. So I'm going to click on the translate in x, and I'll just do like minus 3 millimeters there. And then done. All right, so what this has done is it's kind of positioned the scan relative to the part. If I say hide show meshes and points, you can see there's the scan in pink and you can see the part in blue. You don't have to get them exactly lined up, just close enough. So the point of all this is that we want Live Sinter to compare the shape of the scan to the part, and there'll be little tiny differences in it. And we want it to apply the opposite of those little differences to the negative offset that we printed before, because we know this negative offset produced that scan, and that scan's not perfect. So we can essentially say apply scan adjustment, and Live Sinter is going to perform this operation and show me the results when it's done. So I'm going to let it go ahead and do this operation. At this point, the scan adjustment has taken place, and you can see that the part has been, well, you can't see that it's been tweaked, but you can see from the colors where it has been tweaked. So the orange indicates, orange to red indicates regions where the negative offset shape that we see on the screen has been moved out, away from, outside the original shape. And blue indicates regions that have been moved in a little bit towards the shape. So what this is generally telling me is that the part was scaled up a little bit more, but not everywhere. It was essentially made a little bit bigger in many places on the outside. This kind of tells me that the scan adjustment is compensating for a little bit of shrinkage variation, but it's also not uniform. You can see that on the back of the part, the bottom was actually pushed in a little bit, and on the inside of the cylinder was essentially pushed in a little bit. And so this is going to now result in a shape where if I do an export STL now, it will produce a very slightly altered negative offset shape, similar to the one before, but a little bit different. And if I print this one and sinter it, it should come out closer than the previous scan. So at this point, what I would do is I would save this model under a new name, do a save as, and instead of calling it calibration slug, I'd probably call it calibration slug scan adjustment. And this is because this one contains the first one that I created, the calibration slug, had the negative offset that we ran the first time. This one has the negative offset shape of our first scan adjustment. And you could actually do this multiple times if you wanted to. You could scan it again and bring it in and tweak it again. But what's important is that Live Sinter on the first negative offset gets you 99% of the way there in your negative offset shape. And many times the final shape after doing a Live Sinter negative offset will be so close that you can use it after the first time. But there are some cases where if you want to use a scan adjustment, as we did here, you may decide to further increase the accuracy of your part. So to summarize, if I go back to my picture here that I showed before, what we did here was we applied the scan adjustment, saved the model, exported an STL, and if we print and sinter this, it will come out even closer to the desired shape than what we had done before. Typically, this is for tweaks that are on the order of like 40 to 100 microns at most, because Live Sinter will get you to within 1% typically on the first shot. So this is it's an optional task that you can use if you want to finally tweak your parts. All right, well that wraps up the presentation. I hope this was helpful. Go to desktopmetal.com for more information about Live Sinter. And if you have any questions, please let me know. Thank you.